Every piece of energy we consume on Earth is just recycled star power. Fossil fuels are ancient sunlight stored in the ground. Solar and wind rely on atmospheric patterns driven by the sun. For over 70 years, humanity has been asking a wild question. Instead of waiting for a star's energy to travel 150 million kilometers through space, can we just build a miniature star inside a machine on Earth? To understand the difficulty of that question, look at what we currently use: nuclear fission. Today's power plants fire a neutron at a heavy, unstable atom to split it apart, creating heat and a chain reaction. But it generates highly radioactive waste that must be stored for tens of thousands of years. And if the cooling systems fail, that chain reaction can run away, leading to a catastrophic meltdown. Nuclear fusion does the exact opposite. It takes the lightest elements in the universe and forces them together. There is no chain reaction and zero risk of a meltdown. If a reactor breaches, the reaction stops dead within milliseconds, and the energy density is staggering. Fusing just 1 gram of fuel yields the energy equivalent of burning 11 tons of coal, completely free of carbon emissions. For decades, nuclear fusion was dismissed as a permanent sci-fi pipe dream. The old joke was always that fusion is 30 years away, and always will be. But right now, sudden multi-billion-dollar private investments and historic lab experiments yielding a net energy gain are breaking that timeline. We have moved beyond the stage of theoretical physics. Today, fusion has matured into a ruthless engineering race. The grand physical barrier keeping us from limitless power is that atoms do not want to fuse. Atomic nuclei are packed with positively charged protons. If you try to push them together, they experience electrostatic repulsion, bouncing off each other like the matching positive ends of 2 powerful magnets. To overcome that repulsion, you have to force them to collide at extreme speeds. That requires turning the fuel into a roaring, high-energy soup of stripped nuclei and free electrons, called plasma, and heating it to over 150 million degrees Celsius, literally 10 times hotter than the core of our sun. The central engineering problem: no physical material on Earth can hold a 150 million degree fire without melting instantly. So scientists developed approach A, magnetic confinement. Because plasma is electrically charged, powerful magnetic fields can shape it and suspend it inside a vacuum chamber, touching nothing but empty space. The most mature version is the tokamak. These state-funded megaprojects use massive superconducting coils to twist highly dense plasma into a donut shape. But there is a second camp. Approach B is inertial confinement. Instead of holding a low-density plasma in a magnetic bottle for long periods, facilities take 192 of the world's most powerful lasers and blast them into a peppercorn-sized fuel pellet. The lasers generate a massive flash of X-rays. The outer shell of the pellet vaporizes, forcing a violent, instantaneous inward explosion. This compresses the fuel to 100 times the density of lead, igniting it in a fraction of a billionth of a second. Despite radically different architectures, giant magnetic loops versus precise laser blasts, humanity has proven the math. We know how to trap and ignite a star. In fact, the laser method recently achieved historic scientific break-even. For the first time, researchers got more energy out of the plasma than the lasers put into heating it. This chart shows exactly what happened. They fired 2.05 megajoules of laser energy in and harvested a higher output of 3.15 megajoules. That gives us a scientific Q factor greater than 1. But there is a massive engineering catch that the headlines ignore, known as wall plug efficiency. While the plasma gained energy, powering up those 192 lasers required roughly 300 to 400 megajoules of electricity straight from the grid. To build a practical power plant, you have to cover the electrical draw of the entire facility, the cooling systems, the heavy magnets, all of it. For commercial viability, the overall facility needs an engineering Q factor of 10 or higher. Closing this total energy deficit is the only way to move fusion out of the laboratory and onto the power grid. The realization of this wall plug deficit has changed the landscape entirely. Over 50 private companies have emerged, abandoning slow government timelines to race for grid viability by 2026. Startups like Commonwealth Fusion Systems are revolutionizing the space. They developed high-temperature superconducting magnets that generate fields 13 times stronger than a standard hospital MRI. Because confinement strength scales exponentially with the magnetic field, they can drastically shrink the footprint of a commercial reactor. Others are bypassing the old mechanics entirely. Helion energy fires two high-speed plasma rings at each other. Instead of using the resulting heat to boil water and turn an inefficient steam turbine, their reactor directly captures electricity back through its magnetic coils as the fusion plasma expands, and they have the capital to move fast. These commercial attempts are backed by billions of dollars from major tech investors like OpenAI's Sam Altman, who desperately need massive, clean power sources for data centers. 34-nation megaprojects were absolutely necessary to prove the underlying math. But it is these highly funded, extremely specialized private startups that will actually cross the commercial finish line. However, running a commercial plant requires solving a final set of non-plasma supply chain issues. First is the tritium supply crisis. The fuel is incredibly rare, so future reactors must be engineered with breeding blankets, lining the inside walls with lithium so the reactor actually breeds its own fuel on the fly. Second is the destructive reality of material degradation. The fast neutrons produced in the reaction carry 80% of the energy. Because they have no electric charge, they fly straight through the magnetic fields and smash directly into the solid structural walls. Over time, this intense radioactive bombardment weakens standard metals. The current race is in material science, developing advanced, resilient elements like tungsten alloys, or even liquid lithium walls that can survive the continuous impact. The primary challenge of our generation has moved past the lab. We know how to ignite a star. The real test is building a cage resilient enough to hold it for the world.